we know this can go backwards, right? So obviously this is not, there is no time reversal symmetry, it seems here. But this is a time reversal this is a limitation of time reversal symmetry which has nothing to do with any fundamental physics, but it has to do with the fact that we start with a fairly simple motion, and then we have many degrees of freedom, all these waves and all these interactions in the air and in the water. And in order to have this time reverse process, all these many excitations of air and water and whatsoever, they would have to run backwards with the right phases, and we know this is extremely unlikely if one calculates the probability for the reversal of the process. It forbids itself, and but it's not in principle irreversibility, it's a statistical irreversibility. So such processes are effectively not observed, although in principle they could not be excluded. Okay, so time reversal symmetry is easier in simple systems when you don't have so many degrees of freedom. If you want to do time reversal symmetry in more complex systems, you have to work somewhat harder. So there are exceptions, as we all know. One is in high-energy physics, where time reversal symmetry is broken. I think it has not been observed directly, but PC symmetry is broken, and we all believe that together with time reversal, there is an overall symmetry, PCT symmetry. Another case where time reversal symmetry is broken is the quantum measurement process. There is something weird happening in the quantum measurement process that we struggle with. Some people call it the collapse of the wave function, some people call it the projection that happens when you do a quantum measurement. So definitely this is something that doesn't go in the reverse direction. You have a quantum system with a wave function telling you possible outcomes, probabilities for possible outcomes of a measurement, and then the measurement will give one result, and then you kind of lose information. So it's obvious that this is not time that this cannot be time reversed. Here I also said once you have losses, if you lose energy somehow, then this typically leads to irreversibility. But I put it in brackets because losses are only losses as long as you don't control enough of the environment. So if your system that you control includes the environment, the heat bath, if you have full control of everything, then instead of having losses, you will have quantum entanglement between different objects. Okay, so after this prologue, we come to optics, and we want to apply time reversal symmetry to cases in optics. And just to start off with some simple mathematics, we can, in optics or in quantum physics, we can do the following calculation. We start off with a wave function, and we then have a time evolution, so this is the quantum formalism. And the wave function after a certain time can be calculated from the initial wave function by applying the time evolution operator. Then, if you then apply time reversal operator, this will turn t equal to minus t. And the time evolution operator is this t is the only place where t appears if the Hamiltonian is time independent. If it's time dependent, you can go through the same argument, it's only a bit more complicated. And then if you let the system evolve for a second period of time, equally long, then again you have this time evolution, and it cancels with this term, and you are back to the initial system. So basically what this means that whenever you have a unitary evolution, it can be reversed. So the recipe that we want to use now is that we first prepare the system that in the desired state. So we somehow prepare the final state, but not necessarily with a high efficiency. Then we let the system evolve and determine the final state of this evolution. And then we, when we know this, we can come up with a time-reversed version of the state of this system, and then we can let it go backwards. So this initial study of the free evolution, if we know the system well enough, we can do this in theory, in a Gedanken experiment, in a model, or we can also do it in experiment, but we start out with a not so efficient preparation of this final state and let the system go. And learn about the evolution and then learn which state to prepare so that it goes back, but this time very efficiently. Okay, so the first example is coupling into the fiber. I think, I'm not sure, I don't see the fiber from here. Do you see the fiber in the back? There should be a little bit of shading. Oh, so there should be a fiber around here. So this is the core guiding the light. And this is the end of the fiber. And then we have the diffraction limited divergence. And you can, so this is how the system evolves. You can apply the recipe before the lens, but it's even simpler if you apply the recipe after the lens. So if the lens now, suppose the lens collimates the beam nicely, you just set a collimated beam at the output here. So what you need to do is time reverse this field, and this case is very simple. You just let it go in the opposite direction, and then you will couple very efficiently to the fiber. So in order to couple efficiently, you have to match the numerical aperture of this fiber, but if you, for example, in the back very inefficiently couple in a little bit of light at the output, this will come out with the proper numerical aperture, of course, and so when you then go to the time reverse version, you will couple very efficiently. Okay, example number 2. Let's have a light beam and a mirror, and have a transmitted beam and a reflected beam. So first, the light is on the input side of the mirror, then let's suppose we have pulses, and then with 2 pulses on the 2 output ports. Time reversal would now mean that we send these 2 light beams back, but we also have to be careful that we choose the phase properly. And time reversal has to do with phase conjugations that we have to keep in mind, because eventually, if these 2 beams go back, time reversal, if you do the time reversal properly, then there will be no reflection here, and everything will be transmitted in the direction where it came from. And of course, this happens only if the phase is right. This time reversal symmetry applied to a beam splitter I was surprised to see that this has been used more than 150 years ago by George Gabriel Stokes. I hadn't expected this because I thought this is such a modern tool, but already Gabriel George Stokes used this. He also used to talk about the time reversed wave. He used phase conjugation, but he does not use our notation about complex numbers describing the amplitude and phase of the field, but he talks about sine part of the wave, the cosine part of the wave, and changes the sign of the sine wave, but not of the cosine wave, just as it should be. Okay, so when you go through this example, and you have transmission and reflection coefficients, then you have to, this time reversal symmetry argument can tell you something about the phases that appear upon reflection and transmission at the beam splitter. So the phases are R of rho, and of T the phase is tau. So So one can show that the tau should be the same no matter whether you come from the right or from the left. Rho is not the reflectivity is not necessarily the same. We know in Fresnel coefficients, for example, that you can have a 180-degree phase shift upon reflection if you come from the optically less dense medium. And if you go through this argument and follow Gabor-Jones-Stokes, you find that the phase for the two reflections add up to 180 degrees, and there are several possible solutions, and there are different types of beam splitters. For example, a very thin lamella will be symmetric, so rho 1 and rho 2 should be the same. So then one uses just an I for pi over 2 phase. Or if you have all are real, like in Fresnel equation, then one can be pi and the other one is 0, or anything in between. But it puts a boundary, a restriction on what the phases in the beam splitter can be. Okay, let's go to an optical diode. An optical diode is a device where you can isolate a laser from back reflection of light from the experiment. So the light beam goes through the optical diode in one direction. So the name was borrowed from electronics because light does not go backwards in the opposite direction. How about time reversal symmetry in this case? So the optical diode typically looks like this. You have a polarizer at the input to have to make sure you have a well-defined polarization. So the polarizer transmits this vertical polarization. Then it goes through a Faraday cell, to which a magnetic field is applied, and then the linear polarization is rotated, for example, in the positive direction with respect to the magnetic field. Mathematically positive direction with respect to the magnetic field. And then you add another birefringent object, for example, a quartz cell. This is kind of like a screw-like rotation there. The rotation direction depends on the direction of propagation. So it's more like a screw which you can turn into a nut from, with a right screw will be a right screw no matter whether you come into the nut from the one side or from the other side. So suppose this is just adjusted so that these two compensate. So this turns to the left, this turns back to vertical. Then you will have this vertical light beam coming out. And now in the backward direction, what happens is that the quartz plate turns now in the opposite direction because the k vector changed. So it was a right-hand rotation with respect to the propagation direction. Now the propagation direction changes, so this again is a right-hand rotation. Left is looking from this side. And then you go through the Faraday cell, and here the rotation again goes to the left because it only depends on the magnetic field. And so you'll come back with orthogonal polarization. It doesn't go through the polarizer. This is why this is an optical diode. Now it took a long time for me to tell you what I'm sure you know. But the problem is obviously this time reversal does not work here at first sight. But then one has to think a magnetic field always involves currents. Either you have a magnetic coil and a current goes through some copper coil, or you have molecular atomic currents. In any case, you have electrons which move, and there is a certain direction of velocity involved. And time reversal symmetry, this argument, if you use this, you have to apply it always to the full system. And if you apply it only to a subsystem, you will have this apparent violation. But if you apply it to the full system, and now also change the direction of the current, then the direction of the magnetic field will change, and then the Faraday cell will rotate this backwatch out here. So it will now, with this changed current, it will rotate the polarization back to vertical. And so also in the case of the optical diode, the time reversal argument holds. And A last example of this warm-up is an optical resonator. So there you can ask the question. So what you see here are two optical mirrors combined to form a resonator, and you come up to that resonator from with light from the outside. And the question is, if you use pulse light, can you arrange things such that all the light is inside the resonator? And had you asked me this question maybe 10 years ago, I would have said, well, we all know that the such an interferometer, we learned this in the first year in high school, that in steady state, this can be fully transmitting, but it requires an intensity build-up inside the interferometer so that the back reflection is suppressed by destructive interference between the directly reflected light and the light that leaks out. So the intensity in here has to be correspondingly higher, so that with the small transmission coefficient, the light, the film leaking out is strong enough to compensate for this direct reflection. But this is only in steady state, so I would have said 10 years ago, there will always be some transient part of the pulse be first reflected before you reach steady state, and then you don't have reflection anymore. So you will not be able to put all the energy of the pulse into the Favre-Perot. And but now I appreciate the power of time reversal symmetry, because now we can apply our recipe, and the recipe was, let's think we have this desired state, and that is the light field outside the resonator not excited, but inside the resonator you have a light field at time t equals 0, and then you let the system evolve. And so just to make it simple, I have two mirrors here. One on the one side is 100% mirror, so nothing leaks out there, and there's only one output coupler. You can also tell the story with two output couplers, but it's slightly more complicated, so, but it doesn't change the story. So now in this case with one output coupler, the light will go out in one direction. Of course at first, because of the initial conditions, there will be a sharp rise. It will immediately start transmitting, but as it transmits, as the output coupler transmits light, the intensity inside the resonator will reduce. And so the next moment there will be less light coming out, and as we all know, the solution is an exponential decaying function. And so in the end, you have this exponentially shaped wave packet far away from the resonator, traveling at the speed of light, and the resonator in the end will be empty. And now we understand how time reversal symmetry can help us, because once we have understood how the wave packet looks like that comes out of the resonator, we know what we need to do is we need to send this, the time reversed version of this wave packet back into the resonator. So if we would use a mirror, then the sharp rising edge, which is the leading edge, would reach the resonator first, but that's not the time reversed version. The time reversed version is the one where that part of the wave packet that left the resonator last, this will come back first. So here you have a leading, sharp rising leading edge, and the pulse coming back that you have to prepare to comply with the recipe for time based on time reversal symmetry. This wave packet has to have an exponentially rising leading edge. And if you do this on paper, you go back 100%. And incidentally, there is a close analogy to a single photon, single atom. That's why this was particularly helpful. And because of this close analogy, we also did the experiment to convince ourselves that this is really true. So here's a resonator. Of course, the one side is not 100%, but the reflectivity is much closer to 1 than for the output coupler. So there are these experimental limitations. Here's a laser. There's an acoustic optic modulator to create the exponentially rising wave packet. And then we look at the back reflection of the resonator and look at what